Since you all did all these already, it should be really straightforward and easy to go through and do. Since we already did CF4, I'm not going to do that one again. So let's go ahead and do the NH4. Step 1 is to do what?
Find where it is on the periodic table.
Fair enough. We can find where our elements show up on the periodic table and then total their valence electrons. How many electrons does nitrogen have? Nitrogen brings in 5. Hydrogen brings in 1, but there's 4 of them. Then what do? We multiply it by 4, so I got 5 and I got 4. There's a reason I'm not accepting adding them together.
Subtract 1.
Why subtract 1? You have to account for the charge. With it being a positive charge, that means we had to have lost an electron. We need to subtract 1 from that total, which gets us to a total of 8 electrons. We'll actually use this to prove why we needed to subtract 1 electron in a little bit here. Now what do? You've got to choose a central atom. Central atom in general is the least electronegative. Remember, what we've got up here right now is the abbreviated rules. Which atom is least electronegative? Hydrogen. Hydrogen cannot act as the central atom because hydrogen can only have 1 bond. It cannot bridge. So our central atom must be able to bridge. Hydrogen cannot ever act as a central atom. That means nitrogen is our central atom. We can scatter our hydrogens around it. You'll notice that I scattered them according to what rough shape?
Square.
A square. Why?
Because squares are cool.
Because squares are cool, right? Get it? Squares are... No. All right, Lewis structures based off of a cube. The squares are two-dimensional Lewis structure. Okay. Then what do?
We draw on the electrons all in the inside.
I'm really loving the enthusiasm behind that. Yes, we need to draw in our electrons. Those electrons need to be drawn around nitrogen because
There has to be 8 around the central.
no. The rule is actually up there. We add electrons to nitrogen because it's the most electronegative. That's why we put them around the nitrogen. Yes.
How do you determine the electronegativity?
As far as knowing your electronegativities, there's 2 ways to do that. 1, you pull up a table of electronegativities and you look at it. Okay. 2, which is what you'll have to do on an exam, you have to know the trend for electronegativity. What is your trend?
Whichever spikes higher and spikes lower.
Higher and lower. Our higher electronegativity is our fluorine. Our lower electronegativity is our cesium. Technically francium, but francium falls off the chart because it's so reactive we can't get an electronegativity for it. You'll notice that your noble gases do not have electronegativities because
They're stable.
they're stable. They aren't going to react. And our electronegativities are ultimately looking at how an atom holds bonding electrons. Well, if they never form bonds, there's no point in ranking their ability to hold bonding electrons because they can't form those bonds. Right? What's that?
You can never bond something with helium then?
Helium will never form a bond.
I thought you said bomb at first, and I was really confused.
Bond 007. Yeah, thank you. Somebody's awake. So fluorine, where I already forgot what we're doing. Nitrogen. Nitrogen is closer to fluorine than is hydrogen, so nitrogen's more electronegative than our fluorine, or than our hydrogen. So we should put our electrons around our nitrogen. We'll put them in pairs. We'll again put them in pairs based on that square shape. We've now put in our total electrons, which is 8. That's why we counted it up. Could we have possibly have put in the 9? Why?
Because of the negative charge, or positive charge, sorry.
So let's what we're doing is assuming we forgot the charge. We now have 9 electrons that we'd have to put into the structure. Can we put 9 electrons into the structure? Hydrogen can only accept 2 electrons. Nitrogen can only accept 8 electrons. There's no other place to put electrons on this structure. What would that mean? We totaled our electrons wrong. We'd have to go back and check. Where did we make the mistake? We didn't add the charge accordingly. Okay? So if you forget the charge, sometimes you'll be lucky and you won't be able to account for the electrons properly. Go back, check your total valence electrons, make sure you totaled it correctly. We did total it correctly. It is 8. We now have 8 electrons into our structure. What we now go through and do, any place that we have pairs of electrons between atoms, we can turn it into a line. Usually I go through and actually erase to be cleaner. Those of you that did not erase on the quiz, that's fine. I still understand what you're trying to do. Okay? We've now converted all of our bonds, or all of our pairs of electrons, into lines where they were bonds. We now, to satisfy octets, hydrogen's octet, quote unquote, is 2. It can only fit 2 electrons. Why can it only fit 2 electrons? Not because it's on the edge. It has to do with its electron configuration. In that first energy level, how many electrons fit into the first energy level? Only 2. We can't physically put more than 2 electrons in there. So hydrogen sits only at 2 electrons. Nitrogen in that second energy level, how many electrons fit in the second energy level? 8 electrons. There's our octet. Okay? So we could count our electrons around each hydrogen. You'll notice that there are no non-bonding pairs of electrons. That line represents a bond which was 2 electrons. Those 2 electrons do count for our hydrogen. So each of our hydrogen has 2 electrons. What about our nitrogen? Just like we did for the hydrogen, each of those bonds will count as 2 electrons towards our nitrogen. It's part of that bond, so it gets to count both of those electrons. Yes?
Why is nitrogen in the middle?
Nitrogen is in the middle because in this case, it is the only atom that can bridge. Hydrogen can only form one bond, which means if I put hydrogen in the middle, I can't bridge outwards. I can't connect to any more than one other atom, and there's more than one other atom.
Is that like special just for the hydrogen?
It's for, because it only happens with hydrogen, we can kind of say it's special for hydrogen. When you go out to larger structures, there's other reasons or other factors that allow you to decide how you build your structure. Yeah?
So when we're drawing the structures, we'll draw the lines, but not if there are 2 of the electrons on that same side as the line.
So what that line represents is 2 electrons.
Okay.
That's it.
You wouldn't have both, no. That would be incorrect.
You don't want to show both. Yeah. So that's where I was saying, if you drew it on, because I noticed that I looked at yours carefully enough, you had both. And that's because when we drew it before, that's what I did. Any place I had 2 dots, I just drew a line over the top of it. Officially, you don't want to see the dots anymore, because what does the line represent?
2.
The 2 electrons. So if you draw both the electrons and the dots, you're saying there's 4 electrons in that space, and that's not what you're trying to say.
I remember seeing parallel lines once before.
We'll talk about it. We aren't there yet. Okay. The only time we need to add in more lines is if we need to add them. This is not a structure, we need to add them. Okay. Last step, because this is still officially wrong. We need to account for our formal charge. I know that rule is crossed out, but it's crossed out only because it's given too much detail. All you're responsible for is now acknowledging that this structure is formally charged. Where do we specify charge? Upper right-hand corner. You almost always will see brackets all the way around to signify that that positive charge applies somewhere into that structure. Okay. As you move further through chemistry, you can't just say it applies somewhere to the structure. You have to specify where in the structure. To do that, you would use that formula that's got the nice little line through it to calculate what your formal charge is on every single atom. Yes.
So if your thingy has like the plus in the right hand corner, you have to have it when you draw it out.
You have to draw it when you draw it out. Yep.
If it has a 2+, you have to put 2+.
You have to put 2+. Your charge must maintain the same. You will notice, if you haven't noticed already, I'm kind of lazy. Usually what you'll see me write would be this. Okay? That does not mean 7 plus. That means there's a little bracket there, and I don't want to draw the rest of it. There's the positive charge. Okay? Questions on that one? Oh, yeah. I'm planning on doing them all. And then actually I'm going to throw another one at you after that. It's not on this. No, we're going to do OH minus first. I will do SO3. It'll be there. OH minus. First step. Total valence electrons. How many electrons does oxygen have? 6 electrons. How do we get 6 electrons? So it's in the 6th column. The other option I heard somebody else shout out was 16. Where'd you get the 16 from? If you look at the top of that column, it says 16. Also right next to it, it has the Roman numeral for 6. That's in reference to the number of valence electrons. Okay? So oxygen brings in 6. Hydrogen brings in 1. Because hydrogen is in the first column. Now we can account for the charge. So that's the next step. Charge brings in 1 electron. How do we know 1 electron? Because it's a negative charge. The only way we become negative is by getting more electrons. We total this up and we end up with 8 electrons. Hence the octet. Somebody went through and did this a whole bunch of times and noticed that we kept getting 8 electrons, or multiples of 8. This one's a bit tricky. Which is our center atom?
HO2.
Does it matter? With only 2 atoms, there is no center atom, right? Because there's only 2. To have a center, you need at least 3. Okay, so it doesn't really matter what you decide is your center or not. So we can draw our oxygen, put our hydrogen next to it.
I like H2O.
Now what are we going to do?
Do a line right in the middle.
I want a little bit more than dots. What do you mean put the dots in? The electrons. And I heard valence electrons. You've got to be a little careful with that, because I don't want you putting in the valence electrons of oxygen, because the valence electrons of oxygen is 6. What I want you to put in, the total electrons. So the total electrons in this case is 8. And I'm going to put those electrons around our oxygen first, because oxygen is more electronegative than our hydrogen. I've now accounted for all of my electrons. Now what do I do? Draw a line. Whenever I have electrons between an atom, or between atoms, I can now turn it into a line. How many electrons are around the oxygen? How many electrons are around the hydrogen? 2. Octets are satisfied. I can now move to my formal charge. Okay, there's my cheap little bracket negative sign. You'll notice that I will always circle the charge. Okay, that's just so that I know it's a charge and not an addition multiplication. Yes, then yes.
So you didn't put the 2 electron dots around hydrogen because that line represents
That line,
left side.
exactly right. That line represents 2 electrons that are shared between both the oxygen and the hydrogen, which means both atoms get to count those 2 electrons.
And you typically, when you're drawing the electron dots, would you normally start on the right side though?
Where do you start? Let me ask another question and let's see where we go from there. Where do you start putting electrons? On the most electronegative atom. Is that what you're asking?
No, when you're actually drawing it.
So once I've picked an atom, where do I start putting the electrons on it? Arbitrary. Ultimately, it doesn't matter, because when you put them in, you're putting it in to satisfy the octet, and the octet is 8 electrons. So I will always have those 8 around there. First there was a hand, then.
I was going to ask about the noble gases, so you can go.
Go ahead, Don.
So with this next one, you would draw them, and then there would be lines in between each oxygen because of the.
We'll address that. So for the SO3 is what you're asking about?
Yes, because the oxygen's going to be the base, obviously.
We'll draw that out.
Yeah.
let's hold up on that a little bit. What are you going to ask about the noble gases?
So, if you have like argon negatively charged, still wouldn't be able to bond with like hydrogen?
If you change the oxidation state, change the balance of electrons around those atoms, you can change their bonding.
Sorry.
No, you don't apologize for asking questions, just in general. Right? Unless I get really snappy, in which case I'm just kidding.
So what was your reasoning for only drawing one O and one H? Like, I'm just
That's fine. How many oxygens are in that formula?
one.
How many hydrogens?
One.
1. How would I know that I needed to add 2 hydrogens?
If it's at H2.
Okay. So the subscript tells us how many of each element is there, and that applies only to what's directly in front of it. Okay. We would also see that as H2O. The 2 still only applies to the hydrogen in front. Okay. So your formula tells you how many of those atoms you've got.
For going with that, what if you had O2H2?
Mm-hmm.
Is that possible?
Yep.
Would you have 2 central?
So you again run it, if you have an even number of atoms, you again run into this issue of what is the central atom. Okay. As far as the questions that are asked in lecture, there will be a clear central atom. If it is not clear, then you need to ask. Okay. Raise your hand on the exam, hey, what's the central atom? I don't understand this. Okay. In questions where it might be a bit ambiguous, what you'll see me do is bold the central atom. Okay, and if that still doesn't help you, that's fine. Just raise your hand. I don't know what the central atom is. Good, here it is. This is your central atom. Scatter the rest around. Is this you first, then her?
So in the formula, it doesn't matter where the atoms are placed. Like, it doesn't matter if you have O in front of H or H in front of O.
Yes, it does matter. That falls under IUPAC naming system. And so if you go back to the nomenclature video under covalent, it lists off the order in which your atoms must appear for a covalent bond. So OH2 is technically wrong. H must precede O.
So then would we be wrong when we're drawing this Lewis structure if we put the H?
In the Lewis structure, so here's another fun question. It doesn't matter where we put the H. Okay? So as a sort of example for this, we'll see how well this works. Hopefully you guys don't hate me too much. What's my name? You want to say that a little louder? I don't think everybody heard it. Mike, okay. What's my name now? I at least heard one mic. I'm okay with that. My name doesn't change depending on how you're looking at me. Does this molecule change depending on if I pick it up and just turn it over? No, it's the same compound. Okay? So it does not matter where I place that hydrogen in the Lewis structure. It will become a bit challenging when we move a little bit further on down the road, and we'll talk about that when it becomes a little bit more challenging. Okay? But when we're drawing out Lewis structures, it does not matter where you place that atom on those sides of your square.
Does the double parallel line go in this one now? Second, let's see it.
Okay, so you're really itching to see the double parallel lines, right?
Well, I mean, like,
Okay,
symmetry is...
so it's not in OH minus. So let's make sure, are we all sort of done? Can we move to SO3? Because Don is dying here. In OH minus?
The last one.
In SO3, yeah. That's what we're going to talk about. That's why I want to make sure. Do we have any other questions? Can I move into SO3?
Please do.
Okay. Don is panicking here. Let's get him fixed. Okay. So SO3, how many electrons does sulfur bring in?
6.
How many electrons does oxygen bring in? 6. How many oxygens are there, Anna?
3.
So we have to multiply by 3, and we now have 18. Total is 24. Why did I not add anything for charge? There is no charge, so I don't have to worry about adding or removing electrons. Okay. Where's our central atom? Sulfur is going to be our central atom because, and this gets a little bit weird, they're both kind of close to fluorine without having looked at enough of the electronegativities to see that pattern. Okay. Oxygen is more electronegative than fluorine. Your 3 most electronegative elements are fluorine, oxygen, nitrogen. Those are your most electronegative. Okay, in that order, fluorine being most.
Is neon like 4?
What did we say about our noble gases and electronegativities?
Here when I said
Okay, our noble gases have no electronegativity. For 3 most. Fluorine is the most electronegative. Oxygen is the next. Nitrogen is the next. After that, I have no idea. Maybe chlorine? I don't know. Okay.
Thank you.
Yeah. Do I sound angry? Just checking.
why?
No? Okay, I just want to make sure. I'm not trying to sound angry. I'm trying to sound excited. This is cool stuff. Sulfur is our center atom. Okay. So what do we now do? Scatter the oxygens around it. Okay. I will scatter them again according to the square. Does it matter where I've scattered them? No. Okay, this goes back to what you were asking about. It does not matter where those oxygens are as long as they're on the faces of that square. Okay. Next step.
The electrons around it.
Add the electrons, and we add the electrons starting. Why the oxygens? The most electronegative. Okay. So we can start adding our electrons in. How many do I have now?
Left.
No, how many were total? How many? Whoa. How many are in there now? Yeah, that's. It's like, no, that's the total. How many electrons now? 24. We've got our total electrons. Okay, so now what do? We need to, did you say erase the drawing?
Erase and draw a line.
Erase and draw a line wherever we have a pair of electrons between atoms. So far, so good. Okay, what's the next step? It's not charge. In those previous cases, the satisfying the octet was a really simple check because everything satisfied its octet. How many electrons around the oxygens? 8 around each of them. How many electrons around the sulfur? 6. That is not the octet. Okay. What is our rule? Now we move into this concept of resonance. Okay. And what's happening with resonance is we now need to move electrons towards the sulfur to satisfy its octet. Okay. So there's a couple mistakes that are very common. So let me go through and do the mistakes first. First mistake. Sulfur now has its octet, right? I just put 2 electrons in. What's wrong with that mistake? I've now put in too many electrons. I can only put in 24. So I cannot add 2 more to sulfur. That's not allowed. Next mistake. Okay, well, sulfur needs some electrons, so I'm going to erase them from the oxygen on that right-hand side, and I'm going to give them to the sulfur. Sulfur has its octet now, and I didn't add 2 more electrons. What's wrong with this? Now I've screwed up the oxygen. So I have to move the electrons in such a way that they can count for both atoms. Where do electrons count for both atoms? In a bond. So what I'm going to do is move those 2 electrons now to being in the space between the sulfur and the oxygen. According to rule 5, what do? I can now convert that into a line. And I now have exactly what you were asking about, the 2 parallel lines. What do those 2 parallel lines mean?
Equal sign.
It means I have 2 bonds. So I have a double bond. That's all we're trying to represent with that. What's that?
Is that James Bond's brother?
No. Try that again.
I didn't get it right.
Oh, that's okay. Yeah.
Now, would it matter which
I'm going to break that open in the next second. Any other questions on what we've got drawn? Everybody okay with getting those electrons in to make sure our oxygen and our sulfur have satisfied their octets? Okay. Go ahead.
So we'd still erase the electrons removed though, right?
You still have to erase the electrons that we've moved because they're no longer a lone pair on the oxygen. They are now a bond. Okay, so you do have to make sure that those have been removed from our count because otherwise it'll look like you've added 2 more. Okay. Other questions? Okay. Resonance. Which electrons did I move in to stabilize the sulfur? The electrons from the rightmost oxygen. Did I have to use the electrons from the rightmost oxygen? No. I could have used the electrons from any of the other oxygens. What does that mean I've got? Well, I could have come up with this structure. I know it looks tiny, but I've filled up the rest of it with so much stuff. I might do that in a second. I am going to do that now. Okay. And I could have done this option. Does everybody see those as valid options? Okay. No question. Which of those is the correct answer? All of them. Okay. So if you were asked for this structure, what is the Lewis structure for SO3? You must provide all three of those structures, because all three are equally valid for it. If you provide only one, you're saying the other two are by default wrong, which isn't true. They are all equally valid, so you must draw all three. Yes.
Will that go for every double bonded?
It does not apply to every double bond. I can give you another example where we don't have to worry about resonance. So resonance is a special case. Okay? Anybody moving into organic chemistry, anybody asks you why on a test, your answer for why? Resonance. 70% of the time, you're right. And all you need to do is write resonance, and it's vague enough and correct enough that nobody can take off points. Okay? So if you're ever asked why, resonance. Beautiful answer. Okay? So it is an extremely complex topic, and depending on the structure given, you may have to draw 6 different resonance structures. Okay? How many will you guys have to draw? At most like this, where you've got just 3. Okay? Yes?
Isn't it just all the same then? I mean,
I was waiting for that one too.
like you say, your name is your name no matter which way you say it. I mean,
So when we go through and evaluate these structures, you are absolutely right in considering that. Okay? The difference between these, like for instance, this red one down at the bottom and the purple one. Couldn't I have just taken this structure out, turned it over, and flipped it, and lined it up exactly the same? So aren't they the same? This is where you run into this weird gray area. Yes, they are. That's why you have to draw all 3. Okay? They are different enough from each other that when we're looking at resonance, what we do is we pin the structure. Okay? So when I look at this initial structure right here, the big one in red, okay, it is pinned. I cannot pick it up, flip, or rotate it. Which means if I look at the double bond, where is it on the structure? On the right-hand side. If we look at the other drawing, our purple drawing, where is the double bond? On the left-hand side. When evaluating resonance, our structure is pinned. It cannot be spun, flipped, or rotated, which means those are 2 different resonance structures. Okay? Give me a sec. So another example that we could do on this is if we took a video of me just moving my arm back and forth. Okay? And we just took what is it? Long exposure time. Where's my hand? It's a long exposure. I'm constantly moving. It's going to be blurred. It's in all of those locations. Resonance does not look at a long exposure. Resonance looks at an instant. And if we take an instantaneous picture, my hand appears to be only in one position. What we're trying to draw with our resonance structures is show that motion, that my hand can constantly move in all those locations. The electrons are constantly moving between this oxygen, and this oxygen. Okay? Those electrons in that double bond are shuttling back and forth between all of those equally. Okay? It's a time-lapse photo. We can't draw a time-lapse photo. So we have to draw each of the stops.
So you're saying they all exist at the same time?
They do all exist at the same time. It's not they can, they do. Okay? This is why, again, no one of those structures is correct. You have to have all three. Did see your hand a while ago, sorry.
So let's say you have the top box, and you said it's put on the bottom. Wouldn't that make it have like almost?
So you have to pick kind of your frozen point. And this is why I like the method that I've shown you so far. When we go through, before we even looked at this resonance, that was not the button I wanted to push, but I needed to delete everything anyway. The drawing that I had was this. If you go through and try and put electrons in according to how the textbook may tell you to do it, or according to how a tutor may tell you to do it, you may end up with a situation where you have put your electrons on the sulfur first. One of your oxygens will be missing that pair of electrons. So what do? So, I just share the electrons between the sulfur and the oxygen. Cool. You're now 1/3 correct. But you don't see the pattern on how to get the other 2/3 correct. Does that make sense? The resonance allows you to pick that up. So when we draw this out, that's how we decide our frozen position. There's my frozen skeleton. Now what can I do beyond this to move forward? So if I had instead drawn this, man, I hate drawing these. And love them at the same time. If we'd drawn it this way, now when we go through to draw our resonance structures, the two other structures I will draw will maintain this arrangement of those oxygens. I don't flip and rotate it again, okay? Because that adds another layer on top of it. Okay? For instance, if we're just trying to figure out where my hand is moving up and down right here, where does it look like it's moving? Parallel to you or perpendicular to you? Parallel. Are you sure it's moving parallel? I haven't changed the motion of my hand at all, but to your perspective, it's appeared to change. So we have to be very careful when we're looking at resonance to maintain our perspective. You cannot change that perspective, because if you do, it now looks like something else is happening.
Do we have to worry about where we take the two electrons from, like what side?
From once we've decided that we need to move electrons, so this is a good question, I'm surprised it hasn't come up yet. Let's say we're going to take the electrons from our leftmost oxygen. Which pair of electrons do I take? I need two, but which two? Any one of those two is fair game. Does that change the resonance structure? No. All of those oxygens are equally, or electrons are equally affiliated with the oxygen. I can take any two of those and it will still generate the same resonance structure.
So when you said that we have to show all three,
We
don't
show-
have to show,
Because there's three sources of
Okay,
electrons
but
from three
not-
oxygens.
but we don't
not,
need to show all the different options for
not
the
options
separate-
from an individual
Okay,
atom.
got it.
Yeah. Other questions?
So we had to satisfy the octet by adding another line for this one.
Mhm.
And then for the OH, like, the H only has two. It
Mhm.
shares those two. So how do you, like, because you don't have to make an octet for the H.
True. So there are certain atoms that do not have octets. Okay. There are certain atoms that can exceed their octet. Yeah. There's a reason we have not talked about exceeding the octet. You are not responsible for it. 151 is. Be careful on who you talk to with the tutors. They will show you 151 Lewis structures. Okay? So do not worry about exceeding octets. Okay? And we're going to look at an example on that in a second. But not getting to the octet, there are certain atoms that will not achieve the octet. Hydrogen is one of them. Hydrogen can only have two bonds, period. One bond, two electrons. Break. It's confusing enough. Let's repeat that. Let's try it again. Hydrogen, one bond, only one bond, which means two electrons total around hydrogen, no more. Okay. The next two exceptions might show up in the homework, but will not show up on the exam. Boron and aluminum. Okay. The hydrogen one you might be able to predict only having 2 electrons because it's only in that first energy level. There's only 2 places to put electrons. The boron and the aluminum are tricky. They are happy with only 6 electrons. How do we know that as scientists? We did a bunch of experiments, and in the process of those experiments, we noticed really weird chemistry with boron and aluminum. That weird chemistry is due to the fact that they only want 6 electrons around them. So if you're going through and doing the homework, you might very well come across a problem that has boron or aluminum in it. In fact, I think it shows up in your lab activity. Both of those atoms only want 6 electrons around them, which means at most, how many bonds? 3 bonds. Okay? So you've got 3 exceptions. Hydrogen, 1 bond. Boron, 3 bonds. Aluminum, 3 bonds. Okay? Or hydrogen, 2 electrons. Boron, 6 electrons. Aluminum, 6 electrons. Everything else, you're aiming for an octet, 8 electrons. Okay? And I'm about to do the curveball that you'll see potentially show up both in the homework and at the tutoring center. There was maybe a hand.
Yeah, how does helium have 8 electrons when it only has...
Helium does not have 8 electrons. It has 2 electrons.
8 section?
It's got a full octet. Okay. And so what we're really looking at within that column is a full octet. The bulk of the atoms in that column have 8 electrons. So really hydrogen and helium don't fit super well on the periodic table, okay, as far as their patterning goes. Sometimes you'll actually see them removed off of it because of that. Okay. We ready for the last one? No, I said I got a couple more to throw at you. Number 1, what's this called? SO4 minus 2. Don't tell me SO4 minus 2. That doesn't count. It is sulfate. Okay, not sulfur tetraoxide because it's an ion. We see that -2. As soon as you see an ion, a charge, you're not doing a covalent bond. You're not really doing an ionic bond. You're naming it as an ion. In this case, it's sulfate. Okay. Go through, see what you can come up with for a Lewis structure on this one. Okay. If you got questions, raise your hand. I'll come to you and try and help you get through it. Okay. The first thing that I will show you after we come back from attempting to do this on your own is what the actual Lewis structure is, quote unquote. Okay. And you will compare it back to what you guys have. So let's go ahead and take a look at what the actual answer is. So if you talk to a tutor, you talk to an organic chemist, in theory anybody through 151, they will give you this as an answer. Nobody had that, did you? Okay. The reason you don't have that answer is step 7. Okay. You're not responsible for that extra calculation. That extra calculation tells you that the answer that you guys came up with is not a good answer. Okay. You're not responsible for that last step, which means what do we expect from you? The answer that you should provide on an exam and would get absolute 100% full credit is that one.
Decent.
Okay. If you really want to know more as to why this structure isn't the best one, you can talk to me after class. It really does come down to this actual calculation that you have to go through and test. Okay? You're not responsible for that. What you need to get to is that every atom has its octet. Sulfur has its octet. We do not need double bonds. Okay? Want to make sure you're aware of that because you will see that in the tutoring center if you throw this at some of the tutors. Questions?
Isn't oxygen supposed to be in the center because?
Oxygen's more electronegative. Your center atom needs to be the least electronegative. Okay. Other questions? Yes?
I'm sure corrected, but I'm confused on the bonding between sulfur and the oxygen. Because there's 6 electrons associated with it. We've only got the 4 lines for the bonds.
I'm confused. What do you mean the 6 electrons associated with it?
So looking at the group number or the column number falls under 6, so there should be 6 associated with it, correct?
I see what you're saying. Give me a sec here. So, this is a valid question, and it gets a bit dicey in the response, unfortunately. So we're going to have to kind of do some approximations off of this. When we go through and look at this, your step 1 was to total the valence electrons. Sulfur had 6, oxygen had 6, there's 4 of them. Our charge is -2, so we add 2, and we get a total of 32 electrons. Those 32 electrons need to get scattered into the structure. They get scattered according to the octet. What does that mean about the valence electrons? I don't care. Okay? Your electrons need to get added to the structure to satisfy the octet rule. The octet rule drives everything. It is massively important to draw the proper structure when dealing with the octet. So one of the things that you'll see is your textbook in chapter 5 asks you to draw Lewis structures for an atom, their electron configurations, right? So if we looked at sulfur, If we looked at the sulfur and we looked at its Lewis structure, you probably got something like that, which is that 6 that you're referring to. Well, in that case, there's only 6 electrons that can go into that because it's just a sulfur atom. When we move to SO4 - 2, are there just 6 electrons that I need to worry about? No, there's 32. It's an entirely separate issue. Separate out. The only time that idea of valence electrons and how many electrons get associated with an atom is in step 1. Total your electrons. After that, octet, 8 electrons. Okay? With the 3 exceptions. Okay? Does that answer your question well enough? I know it's a dodge, but unfortunately that's all we can do without getting into it more in depth.
I think that's where the double bonds typically come in 151, right?
Sort of. That's a backhanded way to solve it. But yeah, it does. That's where it does pop up.
Is it just a coincidence that it has 6 for this one specifically because of the 4 single bonds? Or not?
The 4 single bonds have nothing to do with the 6. The 6 valence electrons, why do we know it has 6 valence electrons? Because it's sulfur in that column, in that periodic table. That is the only reason that 6 is associated with the sulfur. It has nothing to do with the structure. Entirely separate can of worms. Okay. One more problem I want to throw at you unless there's questions on this one. Okay. We're going to tag this one. This one's going to be a little bit weird. cH2O. Okay. No. Though an interesting breakdown of that. I like that. Okay. This becomes tricky. Why does this become tricky? We got 3 different atoms, so choosing our center atom is going to be a challenge. But let's hold up on that. Let's deal with the first part. Total the valence electrons. How many valence electrons does carbon have? How many valence electrons does hydrogen have? 1, but there's 2 of them. Oxygen has 6. Our total comes out to 12. All right. Now our step 2, our central atom. This is one that you would potentially see in lab, and you could theoretically come up with your central atom. What do you think the central atom is going to be? Why carbon?
What's the first one?
In our electronegativities, hydrogen is the lowest in electronegativity. But hydrogen can't bridge. So now hydrogen's out of the argument. So now it's between oxygen and carbon. Which one has a lower electronegativity? Carbon. So we pick carbon as our central atom. Now what we try and do is scatter our atoms, the rest of our atoms, around the central atom. Okay? Did I have to do it in that order? No. It just happens to be the one that I like the best. Now what do we do?
Start building single electrons.
Where do we start putting the electrons? On the oxygen. Oxygen needs how many electrons around it? There's my 8. Where do I now put electrons? Hydrogen or carbon? Carbon. Why carbon? Nope. It's the second most electronegative. Put them in according to electronegativities. There's our carbon. We could start putting electrons down here, or our last pair of electrons down there. Why would we not put them there?
So you can pair it.
Because we know we need electrons with the hydrogen. Okay? Yes.
Technically, it really doesn't matter because you're going to notice and draw a line, right? I mean,
So
not
where you run into the technicalities is that technically for this problem, it doesn't matter. But if we change the problem to another example and you start adding it someplace else, and you get it wrong, and then you come back and yell at me why you got it wrong, what I'm going to do is say, did you put the electrons around the next most electronegative atom? Okay? And when you say no, I go, oh, go figure you got it wrong. Probably a little nicer, maybe a little nicer than that. Yes?
Why do you have 8 electrons around oxygen when you designated 6?
The 6 only comes into play when? When totaling the valence electrons, step 1. When I move to adding electrons, I add the electrons until I reach the octet. Always, always, always. So when I start putting electrons around that oxygen, I get to the octet. You have to go to the octet. The only time you count the 6 is in that very first step. After that, every atom needs its octet, period.
Now, does the carbon not follow the octet?
Come back to that in a second. Other questions? Our next step is to do what?
Start bridging.
Pairs of electrons into a line. There's a reason I give you the steps. Follow the steps. Convert our pairs of electrons between atoms into lines. Next step. Satisfy our octets, which is really another way of saying check your octets. How many electrons are around the hydrogens? 2. What's the octet for hydrogen? 2. So it's satisfied. How many electrons are on the oxygen? 8. What's the octet for oxygen? 8. How many electrons are on the carbon? 6. Has it satisfied its octet? No. So this structure is not correct. We need to fix it. How do we fix it? We move electrons towards our carbon to satisfy its octet. We do that by drawing that bond.
Do you have to draw more of this or no? Because it's all
Now the question is, do we have resonance?
No, just one. It's just the one.
Why is there only one structure?
You can't take it from hydrogen.
There's no other pairs of electrons. The only place we've got is the oxygen. So there isn't a resonance structure. So just because you have multiple bonds doesn't mean you have resonance. Okay? We only have resonance if there's multiple sources for those lone pairs. There's only one source.
why is it not just 3 lines? Because wouldn't that mean
3 lines, how many electrons are on the carbon? 6. You have to reach the octet. Have to get the octet. Okay? Octet, octet, octet. Okay, now everybody together. Octet, octet, octet. I didn't hear you enough. Do it again. Once more. Okay, thank you. 8 electrons. You need to have the 8 electrons. Okay? You ready to make this a whole lot worse? How many groups of electrons are around the carbon?
3.
Lewis structures were based on what?
Groups 2.
Cubes. When we draw out our structure on paper, we can't draw a cube. What do we draw? Square. Are there electrons on this face? No. Are there electrons on this face? Are there electrons on this face? Are there electrons on this face? Yes. How many groups of electrons are there? 3. One of those groups happens to be bigger than the other. I don't care. All we're looking at is those 4 faces. Okay? Do we need to be able to acknowledge the groups? Yes. Second part of chapter 12 is now looking at what happens with our Lewis structures in reality. So if we drew out the Lewis structure for CH4 or methane, what would we expect? You should relatively quickly be able to come up with something along those lines. What's the bond angle between the carbon, the hydrogen, and the hydrogen? What you see there is 90. It's not that bad. Come on. That one. That one. I'm being tricky. Why is that a problem? Are any of those carbon to hydrogen bonds different from any of the other carbon to hydrogen bonds? No. So all of those bonds are occupying space in 3 dimensions, and all of them are equally trying to get away from each other, the exact same distance away. If this is an accurate representation of the 3-dimensional model, are they all equal? No. Lewis structures does not represent 3-dimensionality well at all. All it gives you is the proper bonding areas, and that's about it. Okay? To be able to scale higher to understand the 3-dimensional structure, what we have to do is start to look at the arrangement of the electrons around that central atom. And in the case of our methane, we have 4 groups of electrons. If 4 groups are now equally spacing themselves out around a sphere, what shape do we end up with? This is not an easy one to see. A tetrahedron. That is a shape. Yes, that's a shape. Nobody's played D&D? That's a bad question. Maybe I shouldn't ask that. 4-sided die.
Yeah.
4-sided die is a tetrahedron.
Is that what it's called?
Yes. Which, the 4-sided die or a tetrahedron?
4-sided die.
Yeah. 4-sided die is a tetrahedron. Right? Dodecahedron. So, Lewis structures don't represent the 3-dimensional shape well. What we have to do is look at how those electron clouds, the bonds, because those bonds, those lines represent electrons. How do those electrons space themselves relative to each other? Right. How many of you are really great at seeing in 3 dimensions in your head? Yeah, maybe 1 or 2 of you. Good. The 1 or 2 of you that are good at that, guess what? This next section is pretty easy for you. Everybody else, welcome to hell. Okay.
You should have done it.
Or welcome to memorization. So what we have to go through and do is start evaluating the groups of electrons around our central atom and then classify what shape it would come out of it. Because everybody visualizes a shape slightly differently, of course there's now a name associated with that shape. For instance, methane, we refer to that shape as a tetrahedron. You can't call it a 4-sided die. That doesn't count. Okay? We have to refer to it as a tetrahedron. Okay? What happens if we change the groups of electrons? If we move to, say, that last one that we looked at, sorry, trying to not show the three-dimensional shape. How many groups of electrons are now around that carbon? 3. Would I expect the same shape? No. What shape ends up happening here? Trigonal, or trigonal, I'll accept that since that's what you guys are saying. Planar. Because what happens? Those 3 groups of electrons all spread out across the plane. Okay? Yes.
So we'll
Sorry, Don, I'll get back to you.
switch the groups, so if there's 4 groups, it'll always be.
Tetrahedron.
With 4 groups of electrons, it will always be a tetrahedral class.
Tetrahedral class.
Yeah, we'll talk about it in a second. What's up, Don?
Basically, if you have like one side of that has more stuff going on, like one side, that means the surface area gets bigger.
Yes.
That meaning where the shape come in.
Yep. It has to do with that surface area shape. Okay? So, let's address some issues here. It has this big long name associated with it. Valence shell electron pair repulsion theory. Okay? Let's break it down. What did we look at when we looked at the repulsion? We looked at the electrons in bonds repelling away from each other. Where did those electrons come from? What part of the atom? Which part of the electron cloud? The outer levels, which are known as the valence shell electrons, in pairs, because it's a bond, repelling away from each other. Also known as VSEPR. Okay. You end up with 2 classifications out of this, an electron geometry and a molecular geometry. Okay. And yes, we'll talk about that in a second. Okay, so we have those 2 classes. So when you asked, if you have 4 groups of electrons, is it always tetrahedral? It is always a tetrahedral electron geometry. Okay. The molecular geometry is a subcategory that we'll address here in a second. Yes?
It was just, is it valence shell electron or valence electron shell?
Valence shell electron pair repulsion theory.
Okay.
Yeah. You would think the E would swap, but it doesn't. It still said VSEPR. Or I say VSEPR. Okay. Okay. So, you'll notice that everything we've talked about dealt with really 4 groups of electrons because we were looking at a square. Notice how many groups of electrons have we listed? Oh, crap. Because really what happens with a 3-dimensional structure, we have the in and out axis as well. There are technically 6 groups of electrons. Okay. On a cube, you can get 6 groups of electrons. You are responsible for 1 through 4. cHm151 brings in 5 and 6. Trigonal bipyramidal. Yeah. So our names: linear, trigonal planar, tetrahedral. Not responsible, trigonal bipyramidal, octahedral. Okay. It is fun. Okay, so those are our electron geometries. Some of that just comes kind of from sort of obvious things. If we take a look at HF, we look at the Lewis structure for HF. There's H, there's F. What's the shape? There is only one shape. It's a line. It's a linear shape. We're done. Okay. When you move to 2 electron groups, magnesium chloride. Why do we not say dichloride?
No charge. Yeah. It's on the ion.
Let's try the other way. It's not a covalent compound. Our Greek prefixes only come into play for our covalent bonds. Magnesium chloride is not a covalent bond. We end up with 2 groups of electrons around the magnesium. Those electron groups want to get as far away from each other as possible. What do? Turn into a straight line. Okay, so you get that linear shape. After that, it kind of turns into a mess. Right? Yeah, so if you've drawn it, so that's where Lewis structure fails because the other option for magnesium chloride You could have just as easily drawn it this way, right?
Yeah.
Okay, and that's because Lewis structure sucks at drawing three-dimensional structures. So what we would do is if we drew it out this way, we still go through and say how many groups of electrons around it. Well, there's your square. Where do you have groups of electrons? 2 groups, which means linear. Linear. Okay. So your Lewis structure doesn't have to be drawn perfectly. Just count the groups of electrons around it off of the faces of your squares. Do not worry about multiple lines on a multiple face or on a single face. We don't care. It's still one face, one group of electrons.
More than a double bond?
Yes, you can have a triple bond. Okay. Why do we have to take a step further from this? Well, actually, here's some shapes, representations. Ignore the blue parts. What we're looking at is the green and the purple. Those end up giving us those relative shapes. Okay. Why do we have to move to molecular geometry? If we look at the structure of methane, we had 4 groups of electrons, real quickly drawn, right? If we look at the structure for ammonia, NH3, should all be able to very quickly do this, but probably not quite this fast. You end up with this drawing. How many groups of electrons are around ammonia?
4.
Still 4 groups of electrons. So we would predict a tetrahedral shape. But wait, are all of the pairs of electrons around the nitrogen exactly the same? No. You have bonding versus non-bonding. That has to change the shape. Okay? Because now those electrons are being held closer to the atom versus further away because they're shared with another atom. That changes your shape. Okay? So what we need to go through and do is now separate, when we look at our groups of electrons, do we have bonding groups or do we have non-bonding groups? And then evaluate what happens. In molecular geometry, all we care about is the arrangement of the atoms. I don't care about the arrangement of the electrons necessarily, but the electrons force the atoms into certain locations. Okay? So what happens now? We'd start with our standard electron geometries, but we now have to subcategorize out what are the possible ways that a tetrahedron could happen. Well, I could have 4 bonds, okay, and no non-bonding. Or I could have 3 bonds and 1 non-bonding. Or I could have 2 bonds and 2 non-bonding. Or 1 bond and 3 non-bonding. What shape would we have if we only had 1 bond? Linear. What shape would we have if we only had 2 bonds? Remember, the electrons butt in there. They actually prevent the linear shape. We get bent. This one becomes trigonal, but trigonal pyramidal. Okay, because it's not going to be planar, because the electron group is going to block it. What I will try and bring in on Tuesday would be a sequence of models so we can try and see these a little bit cleaner. Okay. Ultimately, your visualization is not that important. What you need to be able to do is recognize the patterns. Anything under this red line, you'll notice that trigonal, bipyramidal, and octahedral turn into a huge cluster mass afterwards. Okay? You aren't responsible for those. You're responsible for everything above tetrahedral and above. Okay? You need to know the subcategory names. This slide right here, I'll tell you that the tutoring center also has it. Please pack up. That's fine. It's okay. This summarizes everything that you would need to do. So you would go through just as we went through, or square your center atom and decide how many groups of electrons. If you're asked electron geometry, it's our first column. If you're asked molecular geometry or molecular shape, evaluate bonding and non-bonding. Categorize, that gets you to your shape.